The next test we're going to take a look at is called the limit comparison test. Now, since it's a comparison test, it's going to work a little bit like our direct comparison test. But the idea here is we're not going to look at a series and compare it directly to another series. We're actually going to look at the limit as one series divided by another series. Now, here's what I mean. Let me go ahead and write down what it says. It says here, if we got the limit as n goes to infinity of, let's say, some a sub n over b sub n is equal to L, where L is some number that falls between 0 and infinity, can't be 0 or infinity. If this is true, then the sum n equals, we'll go from 1 to infinity of a sub n, and the sum n equals 1 to infinity of b sub n do the same thing. Okay, now what do I mean by do the same thing? Well, either they're both going to converge or they're both going to diverge. Here's the idea. As we say, as these things get bigger and bigger and bigger, either they're going to be heading out towards infinity or they're going to be heading towards a value. If they're both heading towards an infinity, well, one may be getting there faster than the other, but that would just be a constant multiple, which means it would be a number. If they're both heading towards a finite value, well, that would both be finite values on top and the bottom, which will also give us a number. However, if one's going to infinity and the other one's not, you could end up with 0 or infinity. That's why it's not particularly helpful. So this actually is going to work a lot like our direct comparison test on how we're going to set it up. So let's just say determine if it converges or diverges. And let's say we have some n equals 1 to infinity. Let's do something like the square root of n over n cubed plus 2. All right, pretty ugly looking here. But we're going to do the same kind of idea that we did with our direct comparison and try to decide whether or not we think this converges or diverges. And we do that the same way. So as n goes to infinity, a sub n, which is the square root of n over n cubed plus 3, looks like, well, that's just going to be the square root of n over n cubed, right? Plus 3 is not going to make any difference as we go to infinity. So what we really want to look at is what does this do? The sum n equals 1 to infinity, n to the 1/2 over n cubed, which is sum n equals 1 to infinity. Let's see, that's 6/2 minus that, so that's 1 over n to the 5/2. Okay, so what do we think that this is going to do here? Well, this is a convergent p-series. So, since we think that that's what this is going to act like as we head out towards infinity, this is what we want to compare it to. So let's do the limit as n goes to infinity. Now, if you notice over here in our definition, it doesn't matter which one's a sub n and which one's b sub n. I didn't state that at all. So I called this one a sub n. That means that this one down here would be our b sub n. Doesn't matter. Generally, the way I do it is I take whichever one's more complicated, which is generally our original one, put that one on the top and the simplified version on the bottom, just for algebra's sake. So here we're going to have the square root of n over n cubed plus 2, all divided by 1 over n to the 5/2. All right, this may take us a little bit of arithmetic, but let's take a look at this. This is going to be the limit as n goes to infinity. This is n to the 1/2 over n cubed plus 2 times n to the 5/2, right? Flip and multiply. So it's the limit as n goes to infinity. If we're multiplying, we have like bases. We're going to add our exponents. So it's going to be 1/2 of 5/2 is 6/2, which is 3 n cubed plus 2. Ooh, a little messy. N cubed over n cubed plus 2. Okay, so what happens to that as n goes to infinity? Now we could stick L'Hopital's rule in here, change it to a continuous variable, make it x's, and do L'Hopital's rule. But the idea here is you can kind of get the idea. As we go to infinity, that's really not going to make any difference, right? The plus 2, so that's really just going to be n cubed over n cubed, which is 1. So in this case, you want to think about it, whatever this is doing the same thing at the exact same rate, right? Because we got a 1 there. So since this is a convergent p-series, that means that this has to also be convergent. So since the sum n equals 1 to infinity of 1 over n to the 5/2 is convergent, then the sum n equals 1 to infinity the square root of n over n cubed plus 2 is also convergent. Okay, so the idea here is if you do the limit between the two series, or a sub n, b sub n's that you're looking at, and you get a finite value falling between 0 and infinity, they're doing the exact same thing. Since we knew what the p-series was doing, we know what this one here is also doing. All right, so pretty easy test. Let's try a couple more here. Let's just get this out of the way. Let's say we have something like the sum n equals 1 to infinity. Let's do 3 over 4 to the n plus 5. Okay, what do we think that this is going to do? Well, as always, let's take a look. As n goes to infinity, our a sub n, which we're calling 3 over 4n plus 5, looks like, well, it could be 3 over 4 to the n. Right, so what does this do? So what is the sum n equals 1 to infinity 3 over 4 to the n? Well, if you've done a bunch of these, hopefully you kind of recognize what that is. I can rewrite that as 3 times 1/4 to the n. Now this is a convergent geometric, right? Here our r is less than 1, or the absolute value of r is less than 1, so we're going to say that's convergent. So we're going to take the limit at the ratio, I'm going to use this one because it's a little bit easier, of these two and see what happens. So let's get this work out of here. All right, what is the limit as n goes to infinity? Again, one of these is going to be our a sub n, one's b sub n. Doesn't matter which one's which. Like I said, I normally put the more complicated one on the top. 4 to the n plus 5, all divided by 3 over 4 to the n. So the limit as n goes to infinity, this is 3 over 4 to the n plus 5 times 4 to the n over 3. So limit as n goes to infinity. Our 3's here can reduce, so we get 4 to the n plus 5. Now again, if we try to do this, of course that's infinity over infinity. We could change to a continuous variable and do L'Hopital's rule, or we can kind of reason our way out of this again, right? As n goes to infinity, plus 5 makes no real difference in this ratio. So that's just going to be 4 to the n over 4 to the n, which is 1. So since we got a finite number that falls between 0 and infinity, whatever one of the series does, the other one does the exact same thing. So since our 3 over 4 to the n was a convergent geometric, that means that this is also convergent. So I'm just going to say, so the sum n equals 1 to infinity, 3 over 4 to the n plus 5 is convergent. Okay, now if we would have gotten 0 or infinity out of this, that doesn't tell us anything. That just means we picked something bad to compare it to. All right, let's try one more here. Let's see, how about sum n equals 1 to infinity, or something to infinity. Let's do 2n over n squared plus 1. All right, so same steps every time here. We'd want to say, what am I going to compare this to? What do I think that this is going to do? So what's happening to this as n goes to infinity? Our a sub n, which is 2 to the n over n squared plus 1, starts to look like or act like just 2 to the n over n squared. right? Because that plus 1 is really not going to make any difference. So what happens to this? The sum n equals 1 to infinity. Now that'll reduce to 2 over n. Well, that's a p-series. This is a divergent p-series. Okay, so since this looks like it's going to act like a divergent p-series, we're going to assume that this also acts like a divergent p-series. Now, you could do this as well. We could have done this on the last one. The 2 is just a constant multiple, so you can think about that as being out front if you wanted to, or not really involved at all. There's nothing wrong with putting the 2 there, by the way. But I'm going to do it with the 1 just to kind of show something different. All right, so let's compare this. Let's do the limit as n goes to infinity, 2n over n squared plus 1, all divided by 1 over n. Limit as n goes to infinity, 2n over n squared plus 1 times n, or n over 1. So it's the limit as n goes to infinity, 2n squared, n squared plus 1. We're in the same situation we've been in a couple times now. We could go to L'Hopital's rule, but again, it kind of makes sense. You know, that plus 1's not going to make any difference. So we'd end up with 2n squared over n squared, which is 2. So, whatever one series is doing, the other one is also doing, because we got a finite number between 0 and infinity. Again, if we would have got 0 or an infinity, either one of those two, that means we chose something poorly to compare it to. We got to pick something else. However, we did get a number between 0 and infinity, so that means these things are doing the same thing. And in this case, since we got a 2, that means this one is actually doing it twice as fast as this one, whatever it's doing. So what are the 2 series doing? Well, we know 1 over n is divergent, so 2n over n squared plus 1 is also divergent, right? So the sum n equals 1 to infinity, 2n over n squared plus 1 is divergent. Okay, so remember, they do the same thing. So just because you get a number out, then you got to interpret that, right? Because we compared it to something that was divergent, it is divergent. If we would have done the same thing and what we compared it to was convergent, our answer would be that it is convergent as long as we get a number that falls between 0 and infinity. Remember, if you do get 0 or infinity, you made a bad choice of what to compare it to. Try something else.